Okay, good morning. There seems to be someone waiting to ask questions or to listen. Anyway, the live session is obviously not a teaching session. Okay? It's a session in which I would like to share interesting anecdotes as well as questions questions which are asked by any of you. Yes, I see the same. There seems to be Shubham Agarwal, and I'm waiting for him to ask the question anyway. Now, while it's going on, I think it's important for me to give some interesting thought processes on chemical bonding. From the history, if we look at, it was Walter Heitler and Fritz London who gave the first theory for the hydrogen molecule using what they call the valence bond method, keeping the idea of Professor Gilbert Newton Lewis, G.N. Lewis, who believed that the valence electrons were important for all of chemistry, and he used the electron dot picture, the octet theory, to advance some of the ideas on chemical bonding before quantum mechanics. But it wasn't so much that Heitler and London who took this farther, but it was Linus Pauling and later Charles Coulson, Robert Mulliken, and in the computational world, it was Professor John Popel and Walter Kohn, who took the idea of quantum chemistry to its full-blown form that we have today. I did share the history of quantum mechanics, I believe, as a lecture note, but as I requested every one of you who are listening to the videos as well as who are contributing, who are learning, to contribute in your own way a bit on the history of quantum chemistry as you come along. And please do that, and please feel free to write to me. Chemical bonding is the reason why most quantum mechanical principles are of interest to chemists. And these cannot be done in a formal way, and formal mathematics has a certain limitation beyond which one needs to get into the numbers. 92 atoms, we can say, limit our current applications of all of the materials in the world, and also in a large part of the universe where we are trying to find out what other elements are there, 92 elements. But of the 92 elements, there are probably 20 to 30 elements which are most common, and the entire organic and living system seem to be limited by less than 10 elements: carbon, nitrogen, hydrogen, oxygen, and probably phosphorus and sulfur. And all the other things are in smaller numbers. But we have more than 30, 40 million molecules. And therefore, the transformation between the various molecules, grouping the molecules to similar properties, all these things are important for chemical bonding. All these things are the reasons why we want to understand chemical bonding, and in the minutest of detail. One concept that I have not expanded in this course so far is the concept of potential energy surface. And that's very important for understanding the molecular reactions and reactions at the elementary level, the chemical physics. The chemical physics of molecules is usually, it's an interface between chemistry and physics, and there are physicists working in the area as well as chemists working in the area, and there are some mathematicians as well. Chemical physics deals with these things at the molecular level, while physical chemistry deals with these things often at the macroscopic, at the measurement level, And therefore, the theories of physical chemistry are often statistical and somewhat average in character. And they address the issue of macroscopic measurement properties. This maybe you can think of as the difference between these two disciplines, that the physical chemists are always concerned with what they see and what they measure, and how the mathematics and the quantum mechanics and the quantum chemistry, as well as the statistical mechanics and even dynamics, can explain larger scale observations. Whereas a chemical physicist usually looks at the microscopic level and looks at the details of the phenomena, and very often looks at the molecular level. Though they may use statistical methods and they may use the classical mechanical methods, their focus is always to look at the details and not gloss over them and obtain measurement properties. Again, these differences between the professions is also, to a point, limited. I mean, you really cannot say one is this or one is that. But a very large number of chemists are looking at it. Today, you can see that organic chemists and inorganic chemists have got into the process of trying to understand computational chemical methods to justify what they see in the laboratory through methods of stability of such molecules using quantum chemistry. So, two areas that I have not concentrated in the first course, this is only a preliminary. One is the computational chemistry. I have not mentioned anything about it. The other is the macroscopic part of it and the chemical bonding that would contribute to the larger scale stability of structures, and also quite far away from what are known as the intermolecular interactions and weak chemical bonds. We have not looked at any of them. Okay. So if there are no questions, I'm still going to continue because there is a certain amount. This is a window of time in which I hope to provide some justification for why you have to learn these things from the point of view that I am focusing. And you can see that this is a similar process in many universities and many postgraduate institutions. Today, you will not be able to do a reasonable amount of research if you haven't spent at least 1 to 2 semesters on the basic principles in the mathematics of quantum mechanics and quantum chemistry. In McGill University, when I started, my professor recommended me to take physics courses on these topics, and he suggested that I would learn better the theory and the methods than merely the applications of them to the chemistry and the chemical problems. Therefore, he recommended me to go to the physics department. That, of course, helped me quite a lot. I think I took probably 5 or 6 courses in the department and in the graduate school of McGill University in Montreal. So I think it is also important for you to keep learning, keep an open mind on what you learn. There is nothing called learning for the purpose of solving a problem. I mean, it looks almost industrious to me. It's more like a specific goal. But as students and as learners, you have to have an open mind. The mathematics of quantum chemistry is very, very important, and there are beautiful books on that. The valence and the chemical aspects and the chemistry of it is so beautifully summarized in some of the modern textbooks and a slightly older but classic books, such as the book by Professor Linus Pauling on the nature of chemical bond, and the quantum mechanics by, surprisingly very old, but it's still very applicable, the book by Linus Pauling himself and Wilson. E. Bright Wilson Jr., who worked with Linus Pauling on many aspects as well as in writing this book together. These 2 American books are among the best that I have found as useful for understanding, but now we have many more good and modern, more recent books, I would say, The book by Donald Macquarie is something I very strongly recommend to every one of you. And if you want to know a little more detail of the calculations done in Macquarie, I would suggest the quantum mechanics book, quantum chemistry book by Levine, I-R-A-E-R-A, Levine. These two take the methods of quantum mechanics and apply them to elementary problems, but a more recent, and a more recent in the sense it's about last 25, 30 years. And a more detailed book on quantum chemistry is the book by Szabo and Ostland. I would have mentioned this in my lecture notes, and if not, I will anyway put these things down in the assignments and other things. Szabo and Ostland's quantum chemistry book is probably the book to learn the next level of quantum chemistry that follows this course. It's also 9 weeks. You have been with me. For a massive open online course program, 9 weeks is too long. Most people would have dropped out by this time to do other things because they have heard something and they've looked at some of them, they understand a bit, and then they don't have the time to understand, or they don't have the time to look at it in detail. They go away, but a course is a course. Whether it's 9 weeks or 12 weeks, you have to decide on what needs to be taught. And so you have 3 more weeks. Those of you who are staying with the course and who are writing the final examination, I hope you will not be disappointed for having spent the time so much in staying with this course material. There are 3 more weeks. More lecture materials will also be put in the website. And the lectures on hydrogen molecule ion, the detailed one in the last week, please don't worry. I'm not going to be examining on the hydrogen molecule ion calculations. They are meant as additional learning materials for you. That will be small elementary assignments and tutorials associated with that. But if you are concerned with the certificate examination, I can safely say that the lecture on the calculation of the overlap integral, the exchange integral, are for you to study later with more detail. And if you happen to be a physical chemistry student or a theoretical chemistry student, you will need to know how to do these things. Therefore, there are some lectures in the course which are not directly meant for the examinations, and you would see that based on my tutorials. 2 more tutorials are being uploaded today or tomorrow on the elementary aspects of bonding and angular momentum. Now, in quantum chemistry, 2 concepts play the central role. One is the energy and the frequency of transition between the energies due to interactions with radiation or due to interactions with other matter. Okay? The interactions with radiations and the transitions that happen between energy levels in various molecules is the study of spectroscopy. The interaction with other matter through intermolecular interactions and intramolecular interactions and the weak bonding or strong bonding and the properties due to these. This is the study of what is called the condensed matter physics or quantum chemistry of materials. Energy and transitions, they form one group of important properties that we have to follow. Energy cannot be observed directly. Quantum mechanics gives energy eigenvalue as a real eigenvalue. It's the eigenvalue of a Hermitian operator, namely the Hamiltonian operator. Still, we don't measure energies. We measure changes in energies through all the experiments. But the changes in these energies allow us to back calculate the energy levels to a consistent picture in quantum mechanics. And therefore, in that sense, energy is the fundamental property. But it is the frequency which is experimentally measurable. And it is the frequency of transition and the intensity of transition that allows us to interpret molecular properties from experimental observations while we calculate them from ab initio quantum chemistry. Therefore, frequencies are important for us to understand. The other important property in quantum chemistry is the angular momentum. The angular momentum of the electron, due to its occupational status in the atom, and the intrinsic angular momentum of the electron, whether the electron is free or bound. These two, the second one being called the spin angular momentum. These two are important in many of the properties of electron energy level classification, the structure of atom, and classifying the various orbitals associated with any given atom, and so on. Therefore, the spin and the angular momentum is another extremely important fundamental quantity. And in this course, I have taken spin only at a very later stage, introduced spin as an ad hoc quantity, and angular momentum, also the orbital angular momentum of the electron, as a property of the electron, and that it comes directly when you express the hydrogen atom using spherical polar coordinates. The entire angular part of the angular equation of the hydrogen atom Schrodinger equation is basically connected to the square of the angular momentum, L squared. You have seen that in one of the problem sets. Both are important and both are quantized. They do not have arbitrary values. They have specific values, either integral or half integral, or any limited number of integral and half integral sets. And the functions we use to calculate may be finite in number or infinite in number, and so on. Okay, no questions yet. So I'm just waiting to see if there are any specific issues. Otherwise, I'll use this time to tell you things that I could not cover in the lecture also. So the quantization of angular momentum is a fundamental requirement for understanding the spin-orbit interactions. The spin-orbit interactions cannot be understood in the usual sense of going from a classical Hamiltonian to a quantum mechanical Hamiltonian. Spin is intrinsically quantum mechanical, and a proper explanation of spin cannot but be given only with relativistic quantum mechanics, which was first proposed by Professor Dirac. Therefore, spin-orbit interactions require you to understand a bit on the relativistic quantum chemistry and quantum mechanics. That becomes even more important as you go higher up in the atomic number. By the time you start worrying about the properties of transition metals and inner transition metals like the lanthanides and actinides, spin-orbit interaction is very strong and is very important for many of the properties of these systems with a large number of electrons. And there, it is important to use relativistic quantum chemistry and relativistic quantum mechanics to study the properties. But despite all of that, the angular momentum as is a fundamental quantity in quantum mechanics as a whole, and particularly in the electrons and the symmetry principle associated with the electron occupation with quantum numbers, specification of quantum numbers. I'm sure you have heard the statement often in the elementary textbooks, no two electrons can have all the four quantum numbers the same. The four quantum numbers being the principal quantum number, the orbital or azimuthal quantum number, and the magnetic quantum number, N, L, and M, which form the basis for the wave function for the hydrogen atom, the electron in the hydrogen atom. But add to that S, which is not part of the Schrodinger's equation, but is later added as the additional degree of freedom. And with the S, the 4 quantum numbers, we have a way of classifying the electrons into many states, and that is why you have orbitals occupying 2 electrons, each orbital occupying 2 electrons, and so on. But do not picture yourself that the electron is going around the atom. We do not know anything about it. All we know is that when we measure or look out for the electron, we see a density map, depending on where we look at and depending on when we look at. If we repeat the same experiment, we may not necessarily get the same electron density, but if we repeat the experiment many, many, many times, you would be able to tell that what is the probability that the electron will be in this region or in that region. And that's, of course, given as the expectation value, which is nothing but the average value of infinitely large measurements. So again, in quantum mechanics, the second important thing, the first one is that quantization of energy and quantization of angular momentum. The second is, of course, recognizing the fact that anything that you want to specify as a property for the electron may not be consistent with your picture. The example being a trajectory in quantum mechanics. It does not exist. A trajectory essentially means the position at each point and the tangent at that point. Without that, you cannot connect the points in between different points. You need to know how the points travel from point A to point B. So the trajectory of the tangent, which is nothing but the velocity. If you plot position as a function of time, then the slope or the tangent is the velocity. Therefore, velocity is, of course, proportional to the momentum. So the trajectory means knowing the position at every point of time and the velocity of the particle exactly at that point of time, in which direction it is and what is the magnitude and so on. That's not possible exactly in quantum mechanics. Therefore, the second important concept in quantum mechanics is our inability, which is still being disputed by many as our inability to know all the variables associated with the system. But let me not get into the philosophical mode. For a practical calculation, as on today, we all agree that it's not possible for the position and momentum to exist simultaneously as properties with specific measurement values that can be ascribed to them without measuring. Einstein contested this in 1935 with a very beautiful and one of the most fundamental papers in all of quantum mechanics through the argument, and it's known as the Einstein, Podolsky, and Rosen paradox, EPR. Lots of explanations have happened since then, but it was important to be familiar with the idea that the trajectory concept is still being pushed by people by saying that at this point we do not know because we do not know enough variables and there are hidden variables in the system and so on. I don't know the answer. Obviously, I'm also learning. But the second important point in quantum is not the quantization, but the fact that a system can be characterized only by a limited set of variables. In the case of hydrogen atom, if you have to think about it, let me use the screen. Yeah, good. Okay, let me use the screen. In the case of hydrogen atom, when you write the hydrogen atom wave function with 3 quantum numbers, and you write this as E psi n L m, clearly all these quantum numbers are exactly attributes of the system. N is the quantum number characterizing the total energy E. L is the quantum number characterizing the attribute called the L square, the total angular momentum. And m is the quantum number connecting to the attribute of the angular momentum in a chosen direction component of the angular momentum in a specific direction. This direction is often the direction of the magnetic field or the electric field that is applied to the system. But this direction is also a direction of a molecular axis or an atomic axis, if you can give a description, but there is a chosen direction. All these three things simultaneously being specified for understanding the wave function basically tell you that the total Hamiltonian, the angular momentum square, and the angular momentum operator associated with the square of the angular momentum, they commute among themselves. H, L square is 0. H, Lz, the commutator is 0. This is a commutator or anti-commutator, if I may say. And L square, Lz is equal to 0. And later we recognize that S is also a property with S square and Sz, which is given by the quantum numbers IEM, if you remember, that I had written half plus minus a half. So essentially what it means is that characterizing a quantum system uniquely and unambiguously is possible only when the operators associated with the characterization or the labels or the quantum labels, the operators must commute among themselves. This is called as a completely commuting operator basis. Completely commuting basis operators, or commuting set of operators by Dirac. Principles of quantum mechanics. Please look into that. So this is the second part. So first is quantization. Second is number of attributes independent. And the Heisenberg's uncertainty principle, which is the reason why our attributes are limited. Quantization is that of the energy and angular momentum in this context. And third is within these, the dynamics. I have not started describing the time-dependent Schrodinger equation, IH mod d psi by dt is equal to h psi. And the time-dependent interactions essentially mean even the Hamiltonian can also depend on time. And four is measurement through spectroscopic. Spectroscopy is the most important tool for measuring the properties. So all these components have to be understood even cursorily before you can make generalizations about the properties of molecules or atoms. Then the question is, how come many of the scientists in the early days were able to say very accurately the properties of things that they did not know, including Mendeleev, who left holes in the periodic table, gaps in the periodic table, to say there should be some elements around that. And then virtually G.N. Lewis defined the chemical bond without having to worry about the solution of the Schrodinger equation. Well, some of his predictions turned out to be wrong. I mean, the extension to octet theory is quite well known today, that octet theory is of a limited application and so on. But the point is, they were able to visualize. The mathematics, which was described afterwards, has virtually forced us to stop visualizing these things in classical terms, but only be able to compute them using either formulas or using the computer. So is that a negative thing with respect to our intuitive ability to discover nature? I wouldn't think so. The quantum chemistry has allowed us the ability to calculate things reasonably accurately using computers, has come to the point of being able to determine the bacteria's, the DNA sequences in some cases, and the properties of the large-scale drug molecules and so on. And so it is not that the loss of our ability to visualize is a limitation, but the ability to compute is our strength. Let's not worry about what we cannot do. Let's worry about what we can do, which is compute. And therefore, it is important for us to compute all the properties. Okay. Now, while we were in a chat mode, there is a quick question. How do we explain tunneling in terms of electron density? Question number one, Suryansh Kashyap. Okay. See, the idea of tunneling has something to do with your concept of a barrier that cannot be surmounted, and therefore somehow you go through the barrier. That's an association with quantum concept, with the classical view. If you think about the electron density, or if you think about the electron wave, let me explain using a harmonic oscillator as a simple example. Yeah, I'll need the screen. Yeah. A very simple way of writing the electron density, you remember the wave function psi, and the electron density, if you want to write this, is defined for the entire space, d tau, which is dx, dy, dz, or r square, dr, sin theta, d theta, d phi, and so on. This essentially tells us that the electron density is non-zero at all intervals that is the whole universe. The tunneling is an extremely important concept only when we think that the system is in a very low energy, very low or well-defined quantum state. And therefore, we think that the energy being low, if its kinetic energy and potential energy cannot be taken to arbitrary values. That is not true. Because if you write this as T plus V, fundamentally in quantum mechanics, the T does not commute with V. This is kinetic energy. This is potential energy. Therefore, when we say that in the harmonic oscillator and we draw a parabola, okay, when we draw a parabola, we have in picture or in mind a picture that the potential energy can be very precisely defined. We don't have that. Therefore, the idea of a tunneling or the tunneling probability is only when we imagine a barrier and we say that the energy of the system is less than the barrier height. The distribution of that energy into kinetic and potential is rather arbitrary. And the wave function is a wave function that is defined in the entire space. Therefore, if you have to define without this potential energy picture, all we can say is that the wave function for the ground state of a harmonic oscillator is that. Anyway, this is never zero until you reach infinity. Okay? Therefore, the square of this, which defines the probability of the system, at any point is actually in any region is actually non-zero. I don't know why we needed tunneling as a concept other than our allegiance to the classical idea and the barrier, and therefore limited to the barrier. The energy of the particle is this, and the fact that it can be found outside clearly tells you that the concept of barrier is a limitation. The potential energy. The barrier is a classical potential. So the concept of tunneling is essentially the presence of the electron density or the possibility of the electron being observed at all regions in space that is accessible to them, even if that space is not accessible to the particle if it were to obey a classical dynamics. And we know that the particle doesn't obey, the microscopic particle doesn't obey a classical dynamics. And it's a macroscopic particle which is classical. And you know that the tunneling probability, again, if you plot the harmonic oscillator for a very large value, suppose you do that, you see that the fraction of the probability that stays outside the classical region defined by a very precise value of the potential energy. This fraction is so small compared to this fraction at a very low energy. Therefore, the tunneling probability is, of course, defined by, in this case, the tunneling probability for the harmonic oscillator is defined by the integral minus infinity to what I call as the minus x minimum, this one negative, all from here. X minimum, the psi square dx, plus x maximum to minus infinity to plus infinity psi square dx. This is one-dimensional. And in the case of hydrogen electron, the 1s orbital defines an approximate region where the electron density is maximum. But please remember, the mathematical construct is such that the 1s orbital has zero, non-zero electron density probability at a billion light years from the point where the nucleus is. It is still non-zero mathematically, but for all practical reasons, it's anyway zero. Therefore, the concept of the probability extended to the entire infinite space and our visual ability to say that there is a barrier that cannot be crossed, which is a classical barrier, which defines the potential energy very precisely. Those are the reasons why you have to think about tunneling as something outside of the classical region. It's clearly not a classical concept. But the electron density can be described as the region outside of the classically permitted region. And in this case of the harmonic oscillator, the classical permitted region is, of course, half kx square. And if the total energy is all of that, then this is called the x max square, or it's also equal to the half k x minimum square, because it's a square of the x. So outside of this is what you call as the tunneling probability. The same thing with the electron density. In the case of hydrogen atom, that is, the classical potential never goes to 0, except at infinity. Therefore, there is nothing called a tunneling probability for the electron density. But if the hydrogen atom were in motion and were to hit a finite barrier, and then its kinetic energy, its total energy is less than the barrier height, it will still have the probability of being able to be detected outside of the barrier, and that is called the square of that, the wave function is called the density, electron density, for that tunneling probability. Okay, so I hope you got at least a partial answer. Okay. So let me go back to the screen. Yeah, that was one question. Let me wait. When the next question comes in, I have someone here, the project colleague who is taking care of all this, the streaming in probably the most beautiful way I've ever imagined. I mean, 20 years ago when we were describing this process of TEL in 1999, we started the project of TEL. I was part of the very first team. We didn't know how to do it, but we all wanted to be online teachers and also offer online certificates. 1999, we wrote the program, and now it's happening in 2019, thanks to people like Balaji and many others who have contributed to this. Okay, so let me go back a little bit on the topic that I was explaining until the next question shoots up. Okay. Yeah, so the concept of chemical bonding in all of these, that is these four ideas, that the quantization of the properties, the number of independent attributes that we can have, the dynamics of the atoms and molecules in real space and in real potential fields interactions, and then the measurement of them using spectroscopy. In all of this, the concept of bonding retains one important characteristics. It is both local as well as extended. I wouldn't call it non-local. The meaning of the phrase non-local is something different from the regular context. I would say local as well as extended. The local essentially means that the bonding is taken, for example, hydrogen molecule. You have two 1s electrons. And you might have seen in the lecture that the bonding orbital is formed from the product of these two 1-electron orbitals, as well as the fact that these are labeled as 1 and 2 can be interchanged to the labels 2 and 1. And also the possible fact that both the electrons are in one atom while the other is depleted, and both the electrons are in the other atom, they come together. Okay. So these are the four possibilities which give rise to this MO theory, the molecular orbital theory, and the possibility of retaining only these two. The first one, as the strong component towards bonding, gives you the valence bond theory. MO. The second important part in quantum mechanics is the principle of superposition. In very elementary but very accurate way, the principle of superposition is explained by Professor Richard Feynman as one of the fundamental principles of quantum mechanics. Volume 3, lectures on physics. And the first chapter. It's called the double slit experiment. The principle of what is described here as the wave function being described as a linear superposition of different wave amplitudes. Let me write this using the wave amplitudes phi1, C2, phi2. In the double slit experiment, we only worry about two of them, but in chemistry, we worry about this by having, in principle, n equal to 1 to infinity Cn phi n. This is the other extremely important idea. Therefore, the calculation, which can be done with infinite summation analytically, yes, we will do it. If it can be done, it should be done. There's no point in approximating what can be done exactly. Okay? And there is no point in doing exactly something for which approximate results are also very good. Both tell you, one is about the accuracy, the other is about the efficiency of your computation. So given that, this being the exact wave function for any system of appropriately chosen basis sets, the whole question of h psi is equal to E psi seems to be the question of determining these coefficients one after the other. But then the chemists and physicists have applied the principle of variation and also the principle of what is called the methods of perturbation, which I have not talked to you in this course, but maybe in the next course on quantum chemistry sometime I would discuss that. The chemists and physicists have found ways of writing this in the most efficient and most direct manner, wherever possible. In the elementary theory of the molecules, of diatomic molecules and triatomic molecules, the efficient and the direct method is to use the atomic orbitals of the atoms. Atomic orbitals of the atoms, of different atoms, or atomic orbitals of the same atom, and then combine them with the orbitals of different atoms. The first process is a straightforward MO theory. The second process of taking atomic orbitals of the same atom and then doing a simplification is called the method of hybridization, and that's the second method. Okay, let me see. Okay, what is the second question? There are two questions here. So Riyansh is asking the question, can we excite the electron in 1s in hydrogen atom to 2s? And if we do so, will that be called tunneling? The answer is no, but you can excite 1s to 2s with the appropriate radiation. This is a spin, there is no spin transition. It's possible for you to do the 1s to 2s. Of course, you see that in the Lyman and Balmer series in the spectrum of hydrogen even before 1900, because the Lyman series corresponds to transitions from all higher levels, what today we call as 2s, 3s, 4s, etc., to the 1s orbital. Therefore, if the electrons can come down, the electrons can also go up. So spectroscopy radiation can be used to do that. But that's not called the tunneling, because it is only making the electron go to an excited state by the application of energy. So it is a standard process. Second question is by Tejaswini. What is meant by perturbation theory? Okay, let me explain that a little bit before we continue on this. Okay, on a lighter note, an ant biting you is a perturbation you ignore, and you can see the effects in no time. You can worry about it. I wouldn't say the same thing about a snake. That's not a perturbation. That's a very, very serious one. What's the corresponding analogy in science? If, for example, a particle in a one-dimensional box, we write the Hamiltonian as minus h bar square by 2m d square by dx square. Okay. There's no potential energy. V is 0 inside the box. However, let's assume that the particle has a spin. Okay. It has a kinetic energy. Let's assume that the particle has a small spin angular momentum associated with this, and let's introduce a small field, E, electric or magnetic, doesn't matter, usually a magnetic field, because the moment associated with the spin is a magnetic angular momentum for the electron. And the magnetic angular momentum can interact with the electron to give you a small potential energy. But if, for example, the energy of the particle is 1 unit of h square by ml square, or 9, 16, and so on, the introduction of this potential energy, if it changes the particle's energy state very slightly, not by say more than 5 to 10%, then such a potential is usually called perturbation. Mini or minute disturbance. Therefore, the same thing happens also for the hydrogen when it is placed in a magnetic field, the hydrogen atom. If it is placed in a magnetic field and its the energy levels and transitions are studied, you would see that each line that you see in the spectrum, the Lyman spectrum, Balmer spectrum, each of these lines can at the most appear as a small doublet about the center. Such observations are usually associated with perturbations. Also, when we shine light on the system, the radiation or the electromagnetic radiation does not alter the state of the system completely, but it only probes what is happening by exciting the electron, say in the case of hydrogen atom, from 1s to 2s. It doesn't alter the state of the hydrogen atom 1s, 2s structure, etc., to something else. However, if you shine a very large amount of very high energy radiation, the molecule may interact with the radiation directly, and the molecular eigenstates, which are the 1s and 2s states, will be completely altered to what are called the dressed states. Such interactions in which the molecular states are completely changed, that is, the eigenstates are completely transformed due to interactions to a new set of eigenstates. Such interactions are not called perturbations, they are called major interactions, and therefore a new Hamiltonian is required to describe such systems. So a perturbation usually refers to small changes in the energy levels and very small perturbations to the eigenfunctions, but not something as to change the character of the whole eigenfunction or the whole of eigenvalue spectrum. There are many examples of that. Atoms in a very small electric field, atoms in a small magnetic field, atoms in the presence of neighboring atoms which have a small interatomic interactions like the Lennard-Jones or van der Waals type interactions. These interactions are perturbing the atomic states and the molecular states to a very small value. Therefore, we have to recalculate this, and the mathematics of doing that is known as the perturbation theory. Sorry. Okay. So those are the only questions so far. So if that is the case, then let me go back to the screen. Yeah, we are getting there. It's about 5 more minutes, and so I should also be closing this. So if you have any question, please get back to me. Otherwise, you might have to ask again 2 weeks from now. I'm planning to come back again once in the next 2 weeks. Okay. If you want to go back to where I had, okay. So the computation of the dynamics of the state of the system at each and every instant of time, and then making a measurement of it, is what today the chemists and physicists are interested. And of course, the other very useful technique is to calculate any property that can be measured experimentally. If you know the wave function, you can calculate the property by having the operator associated with that property sign and extended over the entire integral. This is for any specific time. If the wave function depends on time, then this is at a given time, and therefore the property can change as a function of time. So these are the things which essentially change our way of doing the mechanics at the microscopic level, as opposed to simply following the Newton's equations or the Hamilton's equations or the other one, the Lagrange's equations. These are physical, these are different theories of discussing the evolution of a system in time for a classical macroscopic observable systems. Now, the last thing I would like to say is that the next level of quantum mechanics, which you might want to, okay, it looks like there is a question, but anyway, let me finish the sentence. The last thing I would like to say is the next level of quantum mechanics is to go into the details of what you have done. So when the theory for elementary description of the hydrogen molecule is given to you, one, make sure that you understand the calculations. It's not possible for you to understand the calculation through a lecture and through maybe even several lectures unless you sit down and do it. Therefore, it is important to take a lecture that you have a confidence and you see that things are coming out well, you are able to understand. Go through the calculations yourself one at a time and try to calculate it, if possible, using a different method that you might find in a different book. Or you are a genius, yes, you find your own method and you calculate them. And if you found a different method and that is not known to others, of course, that is publishing. That's research itself. But the second important step is to actually calculate things in quantum mechanics. The question of should I have to learn quantum mechanics is not something I can answer to you. It's your choice. But if you have to learn quantum mechanics, there are certain tools and certain techniques which are available to you. And what I am providing you is one of them, one of what is known as the standard techniques. Therefore, you can use them. Is it useful to me for my understanding of whatever I do? Depends on what you do. If you are a theorist like me, learning is always useful. You have to keep learning. There's no time that you can stop learning and say, I have learned enough, I don't want to do anymore. At that point, you become deadwood. Therefore, it is important for you to keep learning. But if you are in a profession and learning quantum mechanics in a very short period of time is required for you to do certain work, then don't waste time in doing things which are outside your scope. So you have to identify the purpose for which you need to look into courses like this. And third, if you simply ask the question, do I get benefited? Is there any benefit if I continue to learn whatever I like to learn? As far as possible, focus it. Okay? Learn what is needed at the current hour. If you have a professional requirement, if you have an educational requirement, you have to complete a degree program. At that point, do not try to do things outside of the program. Concentrate on it. Most of us, thanks to the modern medicine, most of us are able to live on an average between 80 to 100 years. Losing a year or two in our pursuit of trying to understand things and learning things and losing a job in a short period of time but focusing is not critical. What is critical is the long-term goal. Therefore, if you lose sight of the long-term goal and what you want to learn, and how you want to learn, then none of these methods will work for you. Therefore, as a personal advice to some of the young students, I say, try and learn whatever is possible for you while you are in college, while you are in an institution doing higher studies. Because if you get to the job, I will tell you 99% of the time you will not have enough time to look into the job requirement and also spend time learning. And third, if you get into your family and you have children and wives or husbands around and others, then you have much more priorities to come in the way, and they're going to take all your time. Then you have to wait until, like me, when I'm about to retire, and our children have gone away and they are on their own, and only the two of us are looking at each other. Yes, we both have lots of time to ourselves. While you are in the class, while you are in the college, learn as much as you can, because that's also the most receptive period of your brain. The first 30 years determine 50% of the Nobel Prizes that have been given so far. Therefore, you are in that age group. Okay, we'll continue this in the next teaching or the streaming sessions. But I would like some of you to come up with questions before, or even write those questions saying, please discuss this question in the streaming session that would come up. That would be very helpful to me. Otherwise, I end up giving what is called a more general lecture. It will become one more lecture among the 50 or 60 lectures that you have. But I would like to answer specific questions if you have. Okay? We'll meet again about 2 weeks from now. Thank you. It's already 1 hour. We'll close the streaming session. Thank you very much.